is recording. Okay, well, welcome everybody. My name is Pedro Diniz. I'm currently with ENESC ID in Lisbon, and I've been co-organizing this series on quantum computing talks with the participation, and obviously the general organization from the Faculty of Engineering of the University of Porto. And it's my pleasure today to introduce Dr. Jason Cong, who is the Volgenau Chair for Engineering Excellence Professor and former Department Chair at the UCLA Computer Science Department, with joint appointment from the Electrical Engineering Department, the Director of Center for Domain-Specific Computing, and the Director for VLSI Architecture, Synthesis, and Technology Laboratory. Dr. Cong's research interests include novel architectures and compilation for customizable computing, synthesis of VLSI circuits and systems, and highly scalable algorithms. He has close to 500 publications in these areas, including 16 Best Paper Awards, 3 10-year Most Influential Paper Awards, and the first paper inducted to the FPGA and Reconfigurable Computing Hall of Fame. He and his former students co-founded AutoESL, which developed the most widely used high-level synthesis tool for FPGAs, renamed Vivado HLS after Xilinx acquisition. He was elected to an IEEE Fellow in 2000, ACM Fellow in 2008, the National Academy of Engineering in 2017, and the National Academy of Inventors in 2020. So it's really not surprising, so to speak, that he's going to be talking about optimal qubit mapping and scheduling for quantum computing, given the background that he has on reconfigurable computing. And that's, by the way, on a personal note, where I first met Jason Cong a long time ago, when we were both participating in a DARPA program precisely to compile high-level programming language to reconfigurable FPGA-based computing substrates. So without any further ado, thank you very much once again, Dr. Cong, for sharing your thoughts on quantum computing with us, obviously, and taking the time to be here with us. Thank you. Take it away, please.
Thank you, Pedro, for the introduction. And good afternoon, everyone. And it's a pleasure to meeting all of you virtually. Actually, not only we're going to have a virtual meeting, we're also going to have a hybrid format. Pedro and I discussed the content of the presentation. It turned out a big part of that I covered last July at the keynote speech, the VLSI symposium that took place in early July. So we decided to play actually a part of that, the keynote, and for the materials which are going to have in common. And then towards the end, I will talk about our latest research, and of course there will be a live Q&A. But before we go there, I first want to just share you about the research program in my group. Pedro's mentioned some of that already. By the way, if you're ever interested to follow up on some of the topics I have talked about today, you should go to this vast.ucla.cs.ucla.edu. That's our web page. So there's a project page, talk about the various kind of activities we have. We have a very active program on acceleration for deep learning in the cloud at the edge computing. The second topic, architecture compilation for quantum computing. It's something I'm going to talk about quite a bit today. And Pedro's mentioned about this customizable domain-specific computing. So there's a lot of emphasis using FPGA as a new class of computing devices, not only as a prototyping device or emulation device, right? So that's where actually Pedro and I has quite a bit of interactions in the past. I appreciate the invitation. With that, we actually talk about we have programs on various kind of applications on the, for example, big data applications and brain research, brain inspired computing, and also near data computing. So that's an overview. That if you click into this, so this actually shows the kind of the range of the program we're doing in quantum computing. Most of them, I will say, is between architecture and design automation. Before that, of course, you have application algorithm development. After that, then you have to generating control signals going to the physical devices. So different people cover different layers of the quantum computing. So that's the range we're going to hear today. So Ray, can you start playing the keynote at this point? I will
Yes,
quit
I
my
will.
share.
I will start now.
So it will be interesting. I'll be in the audience of my own talk for a while. Work in my lab we're doing related to compilation or design automation for quantum computing. Let's see. Okay, so this is the outline of the talk. I'll give a quick introduction, especially for people who are lack of some basic quantum computing background. And then I will talk about what's the opportunity there for quantum compilation or design automation. And then talk about some of our recent work in this area. So first, people probably have been reading the news articles recently. There's a lot of excitement around the advances in quantum computing. We start paying attention in this area around 2015, 2016. At that time, I remember the announced quantum device was from UC Santa Barbara with 4 qubits. And then also shortly after that, I visited the Google, the Venice site where they were actually doing the quantum computing work. But you can see this curve actually is quite, the progress is quite amazing. This is on the exponential side. We have a 4 qubit, 8 qubit, 16, 32, 64. For example, both IBM and Google has around 50 some qubits now. That's on the supercomputing, superconducting technology. There's also startups like Rigetti. It's also in the order of tens of qubits. On trapped ion technology, these are in the order of 10 to 15 qubits. Certainly, it's a lot of progress just in the last few years. Whether we can expect exponential growth like a Moore's law, it's yet to be seen, but at least the promise is there. Right? So you may wonder, what can we do with quantum computer? It's actually has a lot of potential. All of us are very familiar with classical computing, where you have 0 bits and the 1 bits and the binary representation. In quantum computing, you also have the 0 state and the 1 state. However, a qubit can be in a superposition of any combination of them. So it's not just a 0 and a 1, it can be also any combination. So in this sense, that these are just the two extreme points. It's a combination of 0, 1, right? So 0 will be represented as 1, 0. 1 is just a superposition, only 1 to 0, 1. But you can be in anything in between. So you can have multiple qubits, multiple bits, right? In our case, we get a bit stream. However, if you have multiple qubits, and you can come up with so-called tensor product, and now you become a vector from 2 qubits, become a vector of length 4. And in general, if you have n qubits, then we get a vector of the 2 to the n. Remember, the 2 to the n is just the dimension of the Hilbert space. And then you can be in composition, linear superposition of any of these combination of these sort of basic dimensions. So that's why you get 2 to the 2 to the n, that the number grows very quickly. So if you just have this representation, what can we do with that? You can also have very simple gates to manipulate on these qubits. For example, a very simple one is like a bit flip. You can take alpha, beta. Remember, alpha, beta is not just 0 and 1. It's actually any numbers as long as, they have to be normalized. So the alpha square plus beta square equal to 1. But you can actually flip that. So it corresponds to a 2 by 2 matrix operation. There's something called the Hadamard gate, and you can take alpha, beta, and go through this transformation, get a new vector. Phase shift gate is very simple, then you can basically rotate it somewhat. There's 2 particular angles where it's important, pi over 2 and pi over 4, which I'll come to that. In fact, the IBM Qiskit, the U3 gate can be very general. You can actually have 3 degrees of freedom, theta, phi, and the lambda, and then give you a general, basically, gate operation you can apply on any qubit. It's not just a single qubit you have operation. You can also have 2 qubit operation. The simplest one is really the control NOT gate or the CX gate. What it basically says that if the first bit is 0, you don't do anything. So the alpha beta get alpha beta. If the first bit and the second bit got flipped, so gamma delta becomes delta gamma, right? What I want to say is that all these gates are unitary. So basically, you can have this matrix multiply its transpose, but also take the complex conjugate, and you get an identity matrix. That's the definition. So all these transformations are unitary transformations. Then was a very interesting, also very important theorem says that you only need these very simple gates, the H gate, Harman gates, right? The P gates and the T gate. These are 2 special rotations. That the phase gate, and then plus the CX gate. It's universal for quantum computing. You can use it to do any quantum computation you want. So that's sort of a very, very quick 3 minutes introduction to quantum computing. You may say, wow, that's actually difficult. I don't write programs that this way. I don't write it either. So what we hope is that where our background comes in is to do design automation or compilation, to take high-level representation, to come up with these primitive gates, right? Like most of you, my background is all on VLSI design automation. So for today, integrated circuits, we can design the very high levels. Domin talked about in our work on high-level synthesis. With high-level synthesis, you can come up with a system specification in C, C++, or System C. And then we can compile it automatically into VHDL Verilog, right? And then you can further perform logic synthesis to get the logic gates that these are the Boolean equations we learned in our digital logic design classes. These are generic Boolean equations. You want to minimize the number of literals. But when you go to TSMC or Samsung for fabrication, you have to actually map it to a particular set of gate libraries. It's very similar to the quantum gate libraries I talked to you. So that's actually the gate circuit design. And finally, you do place and route, you come up with the circuit, you do the fabrication, right? So, so that's the flow we are very familiar with. What I'm looking at is to see whether we can use a similar flow and to do quantum computation. So if you look at what we can do with quantum computation, we start with applications. You have to solve some interesting problems, otherwise no one will buy quantum computers or use quantum computers. So in the near term, so these are some of the interesting applications. You can do simulation, chemistry simulation. You can do certain optimizations, and machine learning is also being considered. Cryptography, we all heard about it, right? To do the prime factorization. Once you have that, then we do quantum algorithm design. This is a lot of that is just a linear algebra, because you can see that all these gates can be represented by matrices. So once you have that, now the next step is the logic synthesis, or equivalent of a logic synthesis. You want to map it to a sequence gate supported by the architecture. For example, IBM, Google, Rigetti, they all have their own set of gates they support. There's a step I'm going to talk more a lot in today's talk that I call the layout synthesis. You have to decide where to execute this gate and what time you execute this gate. So you determine the basically space-time coordinates of all the gates. And then finally, you come up with control signals that, to control that. So this will be waveforms you apply, and then obviously you will be applying to some physical systems. So for my lab, and so this can be superconductor qubits, trapped ion, silicon-based, or also optical technologies. So my lab on our research focused more on this part, from logic synthesis all the way to sort of the control generation. I will talk about part of the research. For those of you who are interested to see more, you can go to the website I listed here. So let me zoom in to talk about layout synthesis in particular. You can actually write a program for quantum computing. So this is a very simple program corresponding to this circuit diagram, which basically says this X gate, remember that's the gate flip, the bit flip one, is actually at the qubit is Q0. And then there's another gate flip, bit flip at the qubit 1, right? Another Hadamard gate at the qubit 3. And then we do a C0 gate at Q2 and Q3. So this is basically a assembled equivalent for quantum computing. And it will give you a circuit diagram to describe what are the order of operations. So we apply these operations from left to right. And these are the time sequences. You can label each gate by a number. So it's a G0, G1, G2. But that's just how your logical program is written. You can actually execute it on some device, quantum device. Some device has only a few qubits. For example, this IBM QX2 has 5 qubits. The largest one that in terms of superconducting qubits, it's probably the Google Sycamore. That's I think IBM also have an equivalent device. It's 53 qubits. So what you need to do is to decide which logical qubit is executed on which the physical qubit. So you can do this mapping. You can say, I want this Q0 to be on this device, on this qubit, and the Q1 to be on this device. So if you do this mapping, then you can do the execution. Remember this one is the first is the X gate. You can apply the X gate here. You can also have a C0 gate. So this Q2, Q3, and you can actually have this operation. But then if you want to apply another C0 gate, this is actually between Q3 and the Q0. Now we have a problem because Q3 and Q0 are not adjacent. You cannot apply that directly. So what do? You can quit the computation, or you can be a little bit more clever. You swap these two gates. You insert the swap gates, and now you can apply this operation at, between Q0 and the Q3, right? So this the CX or C0 gates has to be on a pair of adjacent qubits. So this is the problem we have to address. You can see this is a very small example, but in general it can be quite complex. For example, this is a small adder gate, and how do we map to that? So the input is a circuit and also a device coupling graph. Basically, that tells you that what pair of the qubits are adjacent. You can have a 2-qubit operations. And then the output is the space-time coordinate of all the gates. And you have to determine that at the what time and also at which place each gate will be executed. The reason I call that the layout synthesis is that for some of you are familiar with the VLSI terminology. First, it's a layout, right? We determine the placement of these qubits. But it also has a synthesis flavor because the scheduling normally is part of a high-level synthesis. In this case, we actually do it together with the layout mapping. So that's why I call that a layout synthesis. Remember that we also have to insert swap gates. Swap gates can be implemented by 3 C0 gates. So, but that's the detail. But logically, you have to swap 2 qubits. We have a number of objectives. You can minimize the depths, additional swaps, fidelities. And then the constraints, you got to execute all the gates, right? And then you also got to respect the dependency. If certain program statement happens first, and then you execute the next statement after that's completed. So what I'm going to talk to you is some of the work we have done on first understanding the gap. How good is the existing layout since this tool works, right? And the second one is our own algorithm to that. And also there's implications on architecture evaluation. So let's talk about the gap analysis. I have a student was very interested in working with me in this area to do compilation quantum computing, the design automation for quantum computing. So before we go, we actually did some survey that you have already quite a number of methods to do this layout synthesis. You have a program, you can do that, you can model that by a dependency graph, you can do the scheduling layer by layer, or you can do it in a more greedy way, gate by gate, right? You can also look at the dependency, how do you optimize, formulate that and optimize the program in more general way. And there's also industry tools there. Remember, these companies, they offer you quantum devices. For example, IBM, you can request an account to run on IBM quantum computers. They have a compilation tool called a Qiskit. Rigetti is a startup company. They have their own QLC, and then the Google, is more recent, is Cirq. This ticket that is interesting. It's done by a startup in Cambridge, UK. They don't own quantum computers, but they provide tools for you to design quantum computers. So very natural question before we jump in, I said maybe these tools are already very good. There's no room for us to write another paper to that. So the first thing is that to measure how good they are. But if you look at the literature, these are all NP-hard problems. How do we know that how far away are they away from optimal solution? But then I will say, wait a second, we have addressed this problem that in VSI design before. And for example, circuit placement is an NP-hard problem. But we want to know how good is the existing circuit placement works. But just to remind you, what's circuit placement problem is that you have a netlist, and with gates, they are all connected, right? If you want to place them on a 2D surface, a grid, this is a silicon surface, and how do you measure the quality of the placement? There's many ways we can measure. One simple way is to minimize the total wire length. How do you measure the wire length of this 4-pin net or the 4-gate net? So use the bounding box wire length. In fact, you use the half parameter of the bounding box. You take the maximum and X and Y locations, and then subtract the minimum X and Y locations. So in this case, the maximum X and maximum Y is 5. So you have 5 plus 5 minus the 3 and minus 3. So that's 4, which is reasonable because this one spans right 2 cells. That the horizontal direction, 2 in vertical direction. So the half parameter of this bounding box is 4. You want to minimize all the half parameters of all the nets. So that's the tricky part because all these nets interact with each other. There's various heuristics proposed, but for a long time we do not know how well this heuristics works, right? So my lab actually come up with an interesting way to construct an arbitrarily large circuit where we know the optimal solution. It sounds very fancy, but in fact, once you understand the concept, the method is quite straightforward. We go the other way, that we construct the circuit, we know the optimal solution. For example, you can say, hey, my circuit has 64 2-pin nets, basically, right, the nets connecting 2 gates. So that's fine. I actually have my circuit, 64 circuit elements. I add these 2-pin connections. You may say, oh, actually, I also have another 12 3-pin connections. That's fine. I'm writing down the 3-pin connections this way. You said I also have some 4-pin connections, some 5-pin connections. But in general, that for an n-pin net connecting to n modules, right? I'm going to do the connection in this square root n by square root n box. So obviously, this is the smallest possible bounding box you can have to accommodate this net. So by construction, this is optimal, right? And the net degree distribution will follow exactly the industry benchmarks. In fact, 15 years ago or so, that we have this competition, IBM contributed the circuits. In IBM circuit, you may have 97% two-pin nets, 3% 2% of three-pin nets, and 1% of four-pin nets. So we will follow exactly the same distribution. And then we can construct the benchmarks up to 2 million placement gates. 2 million, it was just a limit at that time considered to be state-of-the-art size. You can easily scale it. And then we use the circuit to measure both academic tool and the industry tool. We find out, wow, there's a pretty big gap. It's 1.6x to 2.5x, which means that if the optimal wire length is 1, some of the tools are producing 1.6 wire lengths or 2.5 wire lengths. So we published the result. In fact, get a lot of attention. Even EE Time has a feature article covering our research. It says that placement tools are far away because we also report the result on industry tools. So we made these circuits all available on the website, and a lot of download you can see from all the EDA companies, the semiconductor companies, and also all the leading universities. So this also generated a lot of interest. The optimality gap that for QUEKO narrowed down to 20% after 3-4 years. Not only are these artificial circuits, once you zoom in to focus on this problem, it also improved on real circuits. For example, this MPL was the multi-level placer from my lab, and we see that being improved by 30% as we tune to address these QUEKO examples. So 30% is quite a big deal. Remember, if you do one Moore's law scaling, you go from 7 nanometer to 5 nanometer, you get about 30% wire length improvement. So this is just by optimization. We get that. So with that inspiration, so we said, okay, we want to do the same thing for quantum computing. Is it possible? It turned out for layout synthesis, we can apply very similar techniques. So the input is a device graph, and so we want to evaluate up to certain depths, right, the gate density. So how do we do that? How do we construct circuits with optimal depths, quantum circuits with optimal depths? So this is your device graph. Let's say only P0, P1, P1, P3, P3, P4, P2, P1, right? They can have connections. There's no other possible connections. So first step is that we'll grow a so-called a backbone. So we grow a circuit with a dependency chain that, for example, of depth 3. So then in this case, you cannot collapse the circuit any further, like beyond below 3. So that's just the dependency chain. There's all other space available at every time slots. So we'll sprinkle some other gates based on the gate density profile, how many percentage of the single qubit gates, how many percentage of the 2 qubit gates. So we will actually populate that. And then, of course, we're not going to tell you this particular layout. We're going to scramble that and to give you a different name of all the qubits. Then we come up with a circuit. We give you this program as the input, right? So this program is just same as any other quantum programs. We're going to evaluate the existing tools. So the tools we evaluate, first the device we evaluate are these 4 kinds. This is a Rigetti device. And this is the IBM Rochester device. This is IBM Tokyo device. And this is a Google Sycamore device. Some of you heard about this quantum supremacy by Google. Is obviously a Sycamore device. We construct 2 sets of circuits. One is we call near-term feasible, because, for example, in this Google supremacy test, their circuits about depths 40 to 50. So we think that might be feasible. And we also have circuits, we can construct any depths we want, right? So 100 to 900. The density that we follow the profile of a Toffoli case. This is a very important case, or the quantum supremacy experiment from Google. And then the tool we evaluated, we focused more on industry tools, the Cirq from Google, Qiskit from IBM, Qubit from Cambridge Quantum Computing. And also this paper in DAC 18, we chose it because I think they won a competition organized by IBM for layout synthesis. So here's the result. I will say the result is quite surprising. Remember, a VLSI case, now our gap is 1.6 to 2.5. But here, for example, on this Rigetti Aspen4 device, the gap is between a couple of x all the way to 10 to 15x, right? So, and then on Google Signal, you look at this, that this is CQC, this is the IBM, this is Google Cirq. The gap goes from a few x all the way to 45x. So this is a much larger gap. To us, it's very surprising because the circuit we generate are much smaller. There, we generate up to 2 million gates for VLSI placement. Here, I will say that if the depth is just, this is all within 40, 50. And if we do the scalability study, we try larger circuit. That's also, the gap is still there. For example, this is a CQC, this is IBM, Qiskit. And this is a depth ratio. Again, it's not the 2% or 8%. This is a 2x, 8x. It's very significant. So with this information that we say, wow, that's actually a lot of opportunities for optimization. So we zoom in to develop our own optimal layout synthesis algorithm. We call it the OLSQ, stands for optimal layout synthesis for quantum computing. So first I want to convince you the problem is actually quite large. When we look at it, even with all the experience that we have with VLSI design automation. So this problem is because it combines the placement and the scheduling. There's prior work to deal with that. For example, in this DAC 19 paper is the optimal solution. So what it has is that they focus on 2 qubit gates, which is fine because single qubit gates, you don't change the placement information. 2 qubit gates we swap, you can change that. So they introduce these binary decision variables, right? If logic qubit Q is mapped to physical qubit P at gate L, so then you have a 1, otherwise you have a 0. So for example, you can have this physical qubit 0 mapped to logic qubit 0 mapped to physical qubit 2, and at the gate 0, and you can actually have a coordinate value to that. So this right away is 2 to the L2, M, and N. M is the number logical qubit, N is a physical qubit, L2 is the number of 2 qubit gates. Not only that, you also need to model the permutations we have that before and after the gate. The permutation, that's actually a much higher number, right? So, for example, you can actually, before this swap gate and after swap gate, permutation changes. So that needs to be encoded. So right away, you get actually, for each 2 qubit gates, then you get n-factorial permutation variables can be affected by that. So that's a need the pre-computation to actually record this information. So altogether, this is a very high complexity approach to the problem. With this simple adder circuit, they already use over 1,500 variables. So in our method, we have a much more efficient, more compact scale the encoding for the problem. So here is our notation. Remember, I used the term space-time. So that's exactly how we encode the solution. For each gate, that we have 2 variables. One is the space variable. XL says that the word is going to be executed, and TL is the time it will be executed. For single qubit gate, the XL is just the physical qubit is going to be mapped to. And for 2 qubit gates, then the XL is the edge. And then we also have a mapping that so we want to know at time t, where is this logical qubit Q is mapped to. So this is not a binary variable. This actually gives us a location, right? So mapping of a logical qubit 0, and at the time 0 is 3 because it maps to physical qubit 3, right? So that's the mapping we're talking about. It also maps the at the time 1 is also mapped to 3, right? And all the way until after a swap, at the logical qubit 0 at time step 8 is now mapped to qubit 2 now because after swap at the P2, P3. So that's how we encode the information. And then finally, once n is still mapped to 2. We also need to know that have a special variable for the swap. Basically, it says at time t on this edge E, do we have a swap or not? If we have a swap, it's 1. If we don't have a swap, that's actually 0. So this is a binary variable. Otherwise, this pi x t are not binary variables. So if you look at this, this is a lot more compact encoding. It's n to the m times t. It's still quite high, the complexity, but remember, compared to the previous one, that's the 2 to the m times n times t. So this is more scalable. I will show you how we can reduce this complexity further. By the way, you don't expect a polynomial time solution if you want to solve it optimally because the problem is shown to be NP high. So this is, I'm just talking about, at the edge P2, P3, we do have a swap which completing at time 7. So in this case, it's 1, otherwise it's 0. So with these variables, actually we can model the objectives functions very easily. So what do we care about? One is that we care about the depth. So depth is just the maximum of all the TLs. And also we care about the swap counts. Remember, swap count is a binary variable. Do we have a swap at time t or not? We just add them all up together. So that gives the number of swaps. That's also something you want to minimize. And then there's the concept of minimizing or optimizing the fidelity, because not all the qubits are born equal. So there's this paper out of Georgia Tech, and also later on Princeton, was quite revealing. If you measure the fidelity of every qubit in the IBM devices, it changes by days, sometimes even by hours. So you want to redo the mapping to optimize that. So the fidelity is if the Cirq has to work correctly, every gate has to work correctly, right? So you times the fidelity of all the measurement gate, fidelity of all the single qubit gate, fidelity of all the 2 qubit gates, and all the fidelity of all the swap gates. So that's actually our overall fidelity. So it turned out with our notation can be all modeled. Now we can say, what about the constraints? The constraints also, we can model that fairly easily. Remember that at any time t, that logic qubit q will be mapped to some physical qubit p, right? So you have that. And also, all the computation has to be finished by some time t. In fact, this t is something we're going to search. It has to be, you can start with the length, the maximum length of the dependency constraint, right? You can gradually relax that if you cannot find a solution. So that's how we can get the optimal solution. And then you also have to make sure that the validity of the space coordinate, the GL is a physical qubit if it's a single qubit gate, or it's a 2 qubit gates. It has to be an edge, right, in the graph. Remember, you cannot do a 2 qubit operation on the non-adjacent variables, on non-adjacent qubits. So finally, you have to follow the dependency constraint. So if that this gate happens before gate 4 happens before gate 8, then you also make sure that there's a dependency constraint that P8 got to be larger than P4. It should be the injective mapping for 2 qubits. They cannot be mapped to the same physical qubit at the same time. So that's actually that all the constraints we have. You can see these are all low order polynomial time constraints. Then there's also, you want to make sure some consistency among these variables. So mapping implies the space-time coordinates. So what happened here is that if at the time 0, physical qubit 0 is mapped to that, the logical qubit 0 is mapped to physical qubit 3, then so this one is going to be acting on this gate, right, at the time 0. So you will say, if we, at time 0, this qubit is at P3, and then this the gate also happens at the P3. So that's one type of constraint. The second type of constraint is about the swaps. So you can actually swap these 2 qubits. That's the initial swap. But you can, however, you can also swap these 2 qubits. That's fine, except that they cannot be happening at the same time if they share a vertex or share a physical qubit. So in this case, you will say, if at time 7, P2, P3 are already doing a swapping, then P2, P0 cannot be doing a swapping because they share a common physical qubit. You're going to enforce that. And also, you cannot allow swap gates here because there's actually a gate operation between P1 and P0 that happening. So that's not possible. So that also can be enforced for consistency. You can say, if at the time that 8, if at the time 8 that you have a gate at gate of 10, right? This is gate 10 between P1 P2, and the P1 P2 and the P0 that P1 is has non-zero interception, then you cannot have a swap on the at this time between the P0 P1. So you put in this constraint to guarantee that all your specification or the representation are consistent. And then the final thing is that when swap did happen, then you want to make sure you update that your variables. For example, originally this logical qubit 0 at the time 0 is mapped to P3, right? And if there's no swap gates, it's still mapped to P3. However, at this time, at time 8, because there's swap gate before that, you will say, that it's before that is P3, but there's a swap gate between P2 and P3, and that's equal to 1 at time 7. Then at the time 8, logical qubit 0 is mapped to P2 now instead of P3. So you can actually come up with this consistent constraint so that it's a true and complete representation of the layout synthesis problem. So if you look at the summary of the constraints, so these are the everything I talked about. So we end up to be n times t times l, and it's number of physical qubit. T is the execution time, and then the L is the number of gates. So in comparison, the prior work was using n as a logical qubit, which can be a lot larger than physical qubit. And then there's an n factorial because they have to model the permutation, and then they only care about the 2 input gates, so you have the L2 instead of the L. So the key advantage, as I said, now we have only polynomial number of constraints, so it's a lot more efficient. there's also an implication on the complexity result. Now the problem, it can be easily shown to be NP because you come up with a proposal, I can verify that very easily in part of the time. Not only that, many of the previous heuristics, they will process either layer by layer or gate by gate. It's dependent on the initial gate input order. But in our case, we model it as a graph. We model the dependency directly. We don't have to worry about the force dependency is introduced. So in this case, if you do it the layer by layer processing, you actually, or gate by gate processing, you introduce these pseudo constraints. They are not there just because the ordering we follow, this algorithm follows. So they introduce this dependency. So this is actually it's already a very significant reduction, but I want to improve the runtime further. Let's see how we can do that. So you probably noticed that many mapping variables are redundant because the qubit is mapped to a physical qubit. They will stay there for a long, long time until we do a swap, right? So then the idea is that we can say, hey, can we come up with a higher level abstraction? The qubit will stay there until we do a swap. So here's a circuit. If you look at it, maybe we can create, divide it into blocks, block 0 and block 1. The definition of block is that the coordinate within the block will not change, the mapping from logical to physical qubit. They only change after we insert a swap gate, right? So the understanding is that the number of these blocks are much, much fewer than the timestamp. So the variables, now we can still have a mapping space-time swap for each block instead of for each timestamp now. So now we reduce it to 2 blocks instead of 14 timestamp for this very simple example. The reduction can be more dramatic when we come to larger examples. After the swap, and we did not specify how things are scheduled, then you can just do as soon as possible scheduling because it doesn't affect the optimality anymore if you don't consider the swap. You still need to observe the dependency, right? So in taking this view, and I can modify my mathematical programming formulation slightly. In fact, in modality, I changed the bound to be the number of blocks I can have. And mapping, injective mapping, there's no change. You cannot map to the same physical qubit. Dependency, now remember that if you are in the same block, you will get the same block number. So it changes from larger than to larger or equal to. Mapping of the constraint for space-time coordinates, there's no change. Mapping over swap, no change. And so it's not required anymore because swap, we model that separately. So there's no overlap that between swap with the original gates. And mapping transformed by the swap, there's no change. So if you look at this way, and now we reduce it further because the B in practice is a constant. So we can go from NTL to NL. You compare it to the previous work, that's a big reduction, right? That you have an exponential term here with all polynomial, and moreover, it's only polynomial that a physical qubit, which is very limited, you know, it's somewhere between 5 to 50 at this point, 53, and L is the number of gates we have. So here is the result that first having this transition base, I call that OLSQ, is a big improvement, 400x plus an improvement on runtime on the circuit we have. Well, we compare it to Qiskit. Remember, this is the independent commercial tool used for layout synthesis. Also, in our evaluation on this optimality test, they seem to have the best results, so we compare with them. On this small circuit to verify the optimality, and for large arithmetic circuits, for QUEKO circuits, we have somewhere between 50% to 100% reduction. For QUEKO, when I say 100% reduction, is that For QUEKO circuit, you can actually get a solution with zero swap, right? But we can all achieve that. They cannot, so that's why it's 100% reduction. Now with this transition-based method, now runtime is comparable to a heuristic method. For example, this TriQ is from Princeton that was a state-of-art layout synthesis tool. And they focus on fidelity, so we measure on fidelity. We get a 1.7x to all the way to 2.1x reduction. That's all improvement on fidelity. I want to mention is that there is a more recent work just presented maybe 2 or 3 months ago. They used A-star search with admissible heuristic. For those of you who know, if you can guarantee an admissible function, you do get an optimal solution. So their method is optimal for depth, but we don't see a way to be to generalize our method to swap count or fidelity. But I want to mention that still I want to mention it because the runtime is a lot of further improvement. So what are some of the interesting applications we can do with existing quantum computers? It's actually optimization I mentioned earlier is a significant problem. Although I used the adder as an example, arithmetic operation is not a strong point of a quantum computer at this point because we can do it so well with a classical computer. Optimization is, I mean, have many applications. I think a lot of our CAD people care about that. So one well-known problem is the graph maximum cut. I know some of you or some of us worked on min cut problem, but the max cut is equally important and also difficult. So how can we cut the circuit so the cut size is maximized? So it turned out that we can model that with binary variables, 0 and 1, in this case, +1, -1. The way we have that is that we just want to minimize this metric, sum of all the summations over all edges that you have the zj, zk, if zj, zk is an edge. So why that works? Because think about it, if zj and zk are in the same partition, so either they are +1, both of them +1, or both of them -1. So you get a 1. So this term becomes 0. So this term becomes 1 only if one is in one partition, another one is in another partition, because you get -1 times 1, you get a -1. So this one gives you a contribution number 1. So that's why by summation over all edges with this expression, I can see how many are being cut. It turned out this representation, you can think about the electron have 2 spins and the up and down. So that's a very direct mapping to the quantum circuits representation. And then this ZJ, ZK can correspond to 2 qubit gates or the ZZ phase gate. So this ZZ phase gate, actually, if you look at it further, it's a diagonal gate. If it's a diagonal, that's this nice property is commutable. So AB, A times B equal to B times A. So in this case, then it's interesting. If you look at this circuit, for example, Google is working on this problem. They just had a publication early this year in Nature Physics. You have this long dependency chain. However, remember I talked about that these gates are all commutable. And in this case, that you can permute them to get a representation of this kind or realization of this kind, the depth will be smaller. So how do we model this degree of freedom? It turned out in that in our OLSQ algorithm, we can specialize it for quantum optimization, QAOA. So we actually now have 2 kinds of dependency. One is a fake dependency. I call that just a collision. If they share some qubit, obviously you cannot place them executing at the same time unit. However, if this one and this one has no shared qubits, then they can actually be executed at the same time. So we will relax the constraint in this case. But there are some dependency. For example, after this qubit, then you do the measurement, and then and or before this qubit, you have to do a Hardeman gate to apply to all the qubits. So this is a really hard dependency constraint. So by this relaxation, we can still solve it optimally. We can show that we have a 70% reduction on depth and 55% reduction that with Qiskit on this QAOA examples. In fact, Google was relying on Qiskit to do the optimization problem. So before I end, I want to mention some ongoing work. So far, I focused only on the lot.
So shall we stop now, Jason?
But yes,
say,
please.
Okay,
what about can we? Okay. Yeah. Thank you.
Thank you very much.
Okay. I think that part actually works out well. That I was also in the audience and listening to my own talk. That's interesting. What I want to say is that that was in July, and then we have some newer result because I was alluding to in the presentation about the ongoing work. In fact, it's no longer ongoing. We had made quite a bit progress.
Okay.
So if you follow everything so far, is that what we have done is that you give me a list of gates, right? And then we'll come up with the best placement and scheduling for these gates. And you may ask the question, well, how do I come up with the list of gates? Which list is the best possible? So that we call the logic synthesis. You want to decompose the algorithm into a set of gates. In general, it's a very hard problem. And whether it's good or not, it really depends after placement and scheduling, what kind of a result you have. So we have a kind of a twist of the problem saying that, yeah, we do not know what is the best, but let's come up with your list. On the way, we can actually modify your gate as needed. So this modification that come from this observation that a lot of these silicon, the quantum computing vendors, they provide so-called programmable gates. For example, for single qubit gates, you can do gate flip, you can do phase change, but actually you can, some of the vendors provide you with a very general single qubit gate, and with these 3 parameters, zeta, phi, lambda, you can show that captures all that single qubit gate. There's another degree of freedom, but that's enforced by the unitary constraint. Of course, you can have 2 qubit gates that the control gate, but more generally that you can have an arbitrary 2 qubit gates that you can show that it can be decomposed into 3 CNOT gates and interleaved with these general single qubit gates. And what kind of a single qubit gate we'll have, we do not know, but it can be implemented by one of these programmable single qubit gate. So that's the key observation, that if we think about it this way, the question is that how do we minimize number of programmable single qubit gate and a programmable 2 qubit gates we're going to use.
Okay. So I don't know, Jensen, how much more material you want to cover. I'm really concerned that some people are going to start disappearing.
Okay. So maybe let's just jump the result that what we can do with this. So in fact, this is quite common in terms of the application that you can do it with chemistry simulation, QAOA. I talked about it already, and then the very recent work on QC and the quantum neural network. So you have also all have plenty of opportunities for absorption. That let me give you one example on this quantum chemistry simulation. So this is the basic gate you will have. Let's say if you have a swap gate after that, and so you have 2 gates, but however you can carry out the computation. And the result is still of this format, right? It's another 2 qubit gates, and that can be again implemented by the same format. So that's the key insight. So we have that this is the result you have if you have the absorption. For example, the Sabre is a leading heuristic mapper at this point. Oops. And then the QAOA that OLSQ I talked about earlier, you can see another like a 50% from 6 to 4 reduction. The swap count obviously is also quite significant because most of them got absorbed away. And so all of this has an impact on fidelity. If you look at it depend on the size of the QAOA graph we have, also depends on the number of iterations you have. You can see this is actually the improvement that we have. If you go through 5 iterations, your fidelity can really drop to 0.1 or even below. Now, early work was like a 20%. So now we can go to 30% or even a little bit higher. So that's the impact. So that's kind of a latest progress. But,
okay.
With that, I would just say that there's a lot of opportunity. You can see that with quantum computing technologies. And in fact, there's also a lot of opportunities for design automation there as well. This OLSQ I talked about provide a framework for optimal solutions for layout synthesis. We're still building things around that. And there's an opportunity to further combine that with logic synthesis. So I will end here. I'd be happy to take questions. Okay. By the way, my PhD student, Daniel Tan, is also in the audience. And he led most of the work. And he'll be happy to answer some questions directly as well.
Okay. Thank you. Well, thank you very much, Jason, for this presentation. I had a couple quick questions, but I'm going to give the floor to the audience so that they can jump in and ask questions. No.
Yeah, sorry, it goes over time a little bit. And,
no, it's all right. I just didn't want to run the risk of losing people or too many people. So I had let me jump in and ask a question. So you talk a lot about these swaps, and if I understand, you could swap not only qubits but even blocks. So is this swap in practice stable? That is, do you run the risk of decoherence of the qubits when you do the swaps? Or alternatively, are there technologies like ion trapping that are more sensitive to these swaps, or this has never been reported?
Right. First, so what we have been doing is more targeted for the superconducting qubits, right? So there, the topology matters a lot. Right. Ion trap is a different kind of a technology where you can have all-to-all interactions, so that at least for up to a certain size. So there, you don't need swap, right? So but however, for superconducting technology, I don't think swap would be any less reliable than other gates, because you can decompose it into a sequence of primitive gates. I think the 3 CNOT gates, you can use that to implement your swap.
Right. So the other thing that popped in my mind as you were describing this LSQC is, since this is an optimization problem, why not use quantum computing to solve it as well?
That's a good point. So quantum computing or quantum optimization are good for certain things, but are not good for everything. In my opinion, that it's good for things that you do not need to have an arbitrary exact solution. For example, optimization is perfect. If you can get the optimal solution, that's great. If you cannot get optimal solution, a little bit off, it's fine. But for like a qubit mapping, it's a problem that you have to make sure every qubit the map to get every gate got computed, right? That every qubit is executed on different physical qubit at a different time. So those are the very hard absolute constraints, and you cannot really quite approximate. And I think that will be the challenge. And even you use quantum, you probably need some post-processing to clean up. But the post-processing is not necessarily easy.
Right. Gotcha. All right. Well, I don't know if there are any other questions from the audience.
But these are good questions, yeah.
So another quick question. I mean, do you have? I mean, are you currently engaging with companies doing specific things like, for instance, this Polaris company that's doing drug discovery? I mean, they have their own tools. I'm wondering if there's an opportunity there, or they see a benefit of using these optimizations in their work. Because at a given point, we had a presentation here, and Shahar Kenan was essentially saying that, well, we have to approximate our problem because it's simply too large. And I'm wondering if there's an opportunity for some of these techniques in this context. I don't know if you have exploited that vein, so to speak.
Right. We haven't really reached out to those sort of the companies in the application space directly, but probably the most interaction we have is with Google because it's in our neighborhood, right? So they have interest in using both the mapping tool and then some application, like for example, chemistry simulation, which will have an impact to drug discovery. Right. The QAOA. So those are the discussions we have. Okay. Some of these benchmarks that I talked about to measure the optimality of the tool, other companies has used that as well, like the Qiskit I mentioned. This is from Cambridge quantum computing. By the way, they have merged with the Honeywell group. It's a new company now, but they certainly has used the tool to give us feedback. And so we'll say a healthy dialogue there.
Okay, so but this tool is available, I mean, for academia and the
oh yeah. All our tools is not only available, it's also open source. You are welcome to take that and then.
So if we go to the website for the VEST through the VEST, we'll basically get links. Okay, good, perfect. Well, thank you. Well, I don't know if there are any other questions. Who may be monitoring the YouTube channel, because sometimes we have.
There are no questions on YouTube at this point.
Okay. All right, good. So shall we wrap it up?
Sure. But if there are any other further questions, feel free to send me through email.
Okay, good. Well, we'll keep in touch because of these other possible interactions. Thank you very much for taking the time to be with us and guide us through your presentation and these closing remarks. Thank you very much, and thank you, the audience, to holding on until the end to listen to this presentation. Thank you, Jason.